Good morning to everyone. I'm going to present the result we got about the detection, characterization, sizing of hydrogen-induced cracking in pressure vessels using phased array ultrasonic data processing. This work is made in collaboration with the ISAB refinery. They provide all the samples we used for the experimental campaign. As we know, pressure vessels in a biomass environment can have hydrogen sulfide cracking, even though now there are materials that can resist this problem. We have many assets that are to be inspected to see if there are cracks inside, and the size of this crack is important, and the location and the thickness is also important to be detected. Sorry. So the approach used is the fitness for service, and for this reason we need a non-destructive test technique, so we can characterize the defect and know exactly if there is an inclusion inside or an hydrogen-induced cracking. And the National Association of Corrosion Engineers, the document is the 0296, has defined well the different damages caused from the hydrogen sulfide. We have 5 different types of cracks. The one on the left here, is the hydrogen glycerin. It's not yet a crack. The one in the middle is the hydrogen-induced cracking. I will talk about this hydrogen-induced cracking. One is embedded, the other one is surface breaking. It's important also to see the difference between the embedded and the surface breaking, because that's very important for the fitness of service, because they use the fracture mechanics, so it's going to have a difference on the time, the window for the next inspection. And on this picture here, you can see the hydrogen-induced cracking after cutting the samples we used for this experimental campaign. So the technique used mostly are ultrasonic techniques, and there are the traditional ultrasonic technique. They use the longitudinal for the planar defect and the shear waves for the stepwise crack. And the time of flight diffraction is also used, and there are also advanced ultrasonic technique with phased array. And usually the best thing is to use a combination of these techniques, because sometimes if you use a standalone technique, it's not going to give the right answer. So the most important thing is that it doesn't matter what we use, we need to know exactly the characterization and size of the defect. Characterization meaning if there is a flaw, an inclusion, or if there is a hydrogen-induced crack inside the sample. And the size of the defect should include the 3D dimension and the position inside the plate. So we got 4 different samples provided by this refinery, as I said before. And these 4 pieces were cut from pressure vessels at the end of the service life. And the pieces had the thickness range good for the calibration that was done before the experimental campaign. So all 4 pieces were inspected with the same probe, the same setup, the same equipment. The only difference between one and the other was the gain, because the surface condition of the 4 samples were very different. There was paint, there was oxide, and so we had different signal to noise ratio. So we had to up the gain. So we had 4 plates of carbon steel, and we did several scans for each one, so 10 for the first, 8, 5, and 5. So before the experimental campaign, we did calibration measurements. We had a sample with the material that is ultrasonic equivalent to the carbon steel, and we had 3 holes, 1.5 millimeter at different depth. And then we had 4 holes, 2 millimeters and 5 millimeters, again at different depth. That's the flat bottom holes. And then 2 notches to see if we could get the near surface defect. We used the 5 MHz with 64 elements, phased array probe with a wedge, and we used 2 different setups, one with a linear ultrasonic beam at 0 degree, and was focused at 2/3 of the thickness, and the other one was a sectorial with plus minus 30 degree. And they were all good. We could see all the reflectors that were made in the calibration block. After the normal phased array method, we also use the full matrix capture and the total focusing method. So the full matrix capture is a different approach. So there are n elements in the probe. So one is the transmitter and the other n are the receivers, and that happens for all of them. So at the end we'll have a matrix n by n with 8 scans. So each one is a signal, is an A scan. As with the total focusing method, we are able to define well the wave with the maximum amplitude for each pixel defined in the area of interest. The problem, the difference between the normal phased array and this new approach is that the scan speed is reduced. We have a lot of data. So basically these are the results. So we have the full samples. We did the 10, 8, 5, 5 scans, and we reported this information for the test. So we have the type of flow, if it was a planar defect of the stepwise crack, usually the geometry of the hydrogen intrusive cracking. The position, we had an encoder with the probe, so we could see which position was starting the defect. And then we have also the length of the defect, the depth, the height of the stepwise cracking, the thickness in the place where the scan was done. So for the 4 plates, we had a report like this. As I said before, the type of flow. So at the end, we had only two types of stepwise cracking. The other defects were also planar defect, with the position starting from the 0, so the origin of the plate, the length, the depth, and the height of the thickness of the defect, so stepwise crack. So only for scan number 4, scan number 6, that were these 2 type of defect. So these are the information we got. So we have here sectorial scan and the B scan, and the same thing for the sample A. So there was the sample B, the sample A with the linear scan and B scan. After doing the measurements, we also cut the sample to see if there was the right measurement, the right measurements of the defect and the right size. And the only problem with this type of measurements, I'm talking about the phased array, is that the height of the defect is going to be oversized. So we need another approach. That's why we also added to the standard phased array the full metric capture total focusing method. In this way, we are able to get less noise at the end of the external surface compared to the previous one, the one for the phased array, the standard phased array. This is much smaller at the end of the external surface, and we can also do a post-processing of the n per n matrix we got with the full matrix capture, and do different analysis to get the best 3D reconstruction of the signal. So this is the best result that we got with the post-processing done after. Another thing we can do using this good software is reconstruction of the defect. So we can reconstruct the scan we have done, and that's important because we can give a different view and export the geometry and the location of the defect, and that's good to do at the end the fitness for service, and so the fracture mechanics can be really applied quickly. And another important thing with this inspection is that we are able to see if a defect is really hydrogen cracking, or if there is an inclusion, or if there is a suspect hydrogen cracking. The only thing is that we cannot get the full answer looking only at one scan. Doesn't matter if it's a sectorial C scan, B scan, A scan. We need to get all these images and look all of them, because, for instance, in this case, the defect was looking like a near surface hydrogen-induced cracking, but at the end, looking at all these images, we understood there was actually and non-metallic inclusion. Metallic inclusion usually are found more in the middle of the thickness, but in this case they were down because there were no metallic inclusion, but we were not sure. So at the end we cut again the sample, and it was confirmed that this was a non-metallic inclusion. So concluding, the good result we got doing this research is that the phased array is good and can be a good tool if properly designed for the samples that has to be expected. The main problems with the phased array, the normal phased array, is that we get many times false calls. That's the main problem, and also we get an oversize of the height of the defect. But if we use it together with the phased array, also the full metric capture and photofocusing method, we can first of all reduce the dead zone that is on the external surface of the sample, and we can reduce the oversize, get an accurate height sizing of the defect. The other important thing is that with the software, the SIVA, we can reconstruct the geometry of the defect and export the geometry, the shape, the dimension, and the location of the defect in the sample, and then provide this to the fitness service approach. And in this way, the operator that is going to do the inspection will have this further tool to decide and to understand if there is hydrogen-induced cracking or not. Thank you.